So we had already done a lesson on the inverse of a matrix or inverses of matrices. This lesson we want to devote to something called elementary matrices. Elementary matrices. Now David Ley, that's our author. In his book, he looks at elementary matrices on page 108. And pages 108 through 109, that's where he mainly does this. And he doesn't really go into much detail. He doesn't really tell you a whole lot about elementary matrices. This is what? David Ley. That's our author. Elementary matrices. So what we want to do, we want to go into detail about these things, give some definitions. We want to define 3 types of elementary matrices. So elementary matrix definitions is what we're going to introduce. So there are going to be 3 types. I don't know what that's about. Okay. The first type is going to be called the permutation. The permutation elementary matrix. So the permutation matrix, we're going to denote with a Pij. P with subscripts Ij. And basically what that is, that's where you take the identity matrix and you swap out the ith and the jth columns. The ith and the jth columns. So let's put it this way. Pij is the matrix that results from swapping the ith and jth columns of the identity matrix, the n by n identity matrix In. Now if you want to give that a nice notation, in column form, you would start off with epsilon 1, that would be the first column of the identity, epsilon 2, and you keep going, right? You have the columns of the identity until you get to the ith column. What happens in the ith column? Well, remember, we're swapping the ith column and the jth column. So epsilon j is going to go in the ith column. And then everything else is normal, like the identity. And then you get to the jth column, and you get something weird going on. You get epsilon I. Right, we swapped out epsilon I and epsilon j. And then everything's back to normal through epsilon n. Now let's actually look at this. So we want to look at some 3x3 examples. We'll just say 3x3 example. So in each case, we're going to start off with the identity, I3. Right, the 3x3 identity. Epsilon 1 is what? 1, 0, 0. Epsilon 2 is 0, 1, 0. And epsilon 3 is 0, 0, 1. So that's the identity matrix. Now we want to focus on a permutation matrix. Let's call it P sub 1, 2. So what do you do with that? Well, basically, you keep the identity matrix except for the first column and the second column, right? We swap those 2 columns. So you're going to get 0, 1, 0 in the first column and 1, 0, 0 in the second column. And then the third column is going to stay the same, 0, 0, 1. Yeah. So typical permutation example. Let's do another definition. Define a second type of elementary matrix. So we got the permutation. Let's introduce something called a scaling elementary matrix. So you hear the word scaling, you think, multiplying, right? That's what scaling refers to. It's like taking a constant and multiplying. So we're going to call this M sub I of R. M sub I of R, the scaling elementary matrix. So M is for basically multiply. We're going to be multiplying by this scalar called R. We're going to multiply the ith column by R. What ith column? The ith column of the identity matrix. So basically you take the identity matrix and you multiply the ith column by R, and that gives you your scaling elementary matrix. So this is Mi sub R with R not 0, right? Your scalar, you don't want it to be 0. You don't want to multiply by 0. Mi of R with R not 0 is the matrix that results from scaling the ith column of the identity matrix, In, by the scalar R. Now, if you wanted to give this a nice column notation, call this M sub I of R equals, so the first column would be epsilon 1, second column would be epsilon 2, just like the identity, and then you would get to the ith column, and then things would be weird, right? Different. So in the ith column, you would multiply that by R, so you'd have R times epsilon sub I. And then the rest of the columns are all normal epsilons, epsilon through epsilon n. Okay, so a 3x3 example. So I start off with the identity I3, 1, 0, 0, epsilon 1, 0, 1, 0, that's epsilon 2, and 0, 0, 1, that's epsilon 3. And let's say we want to talk about M 2, 5, M sub 2 of 5. So basically, I am going to take this second column right here, I'm going to scale it by 5, scale by 5, this whole second column. So the first column stays 1, 0, 0. The second column we're going to multiply by 5, we're going to get 0, oops, it should be red, 0, 5, 0. And the third column stays the same, 0, 0, 1. So there we have it, M25. That is our scaling elementary matrix. Okay, here's a replacement. This is the last and the final type. The third and the final type, I should say, type of elementary matrix. This one's called the replacement. This one's a little tricky to get right, to say it right. The concept is easy. The concept's really easy, but stating it is a little difficult, so I have to be careful. So the replacement elementary matrix. I often screw it up when I'm stating it. So replacement elementary matrix, we designate this as capital R for guess what? Replacement. Ij, comma R. So R is going to be a scalar, little r. Big R is a matrix, little r is a scalar. So what we're going to do, we're basically going to start off with the identity, and we're going to multiply the jth column. No, I want to say this right. You want to multiply the ith column, okay, by R. So you multiply the ith column by R and add it to the jth column to get a new jth column. So how do we say that? Rij of R is the matrix that results from replacing the jth column of the identity with R times the ith column plus the jth column of the identity. Yeah, that's the way to put it. So R sub ij of little r is the matrix that results from replacing the jth column of the identity matrix with, let me scroll a little bit so I can write some more. with, so we're going to replace the jth column of the identity matrix with r multiplied or scaled by the ith column of the identity plus the jth column of the identity. Okay, that's a mouthful. So let's actually give an example here of a replacement type elementary matrix. Let's say you start off with the identity I3. That has epsilon 1, 1, 0, 0, epsilon 2, 0, 1, 0, epsilon 3, 0, 0, 1. And you want to look at, I don't know, R, it's capital R. Let's do 2, 3 of 5. R, 2, 3 of 5. So according to the definition, we're starting off with the identity, and we're going to multiply the second column by 5, and then add that to the third column and update the third column. So the first column is not going to change, 1, 0, 0. The second column is not going to change, 0, 1, 0. We're going to update the third column. So what do? I multiply the second column by 5 and add it to the third column. So I'm going to have 5 times the second column would be, let's see, 0, 5, 0, and we're going to add that to the third column entry, 0, 0, 1, to get a new third column. So that's going to be, well, let's make it in red. 1, 0, 0, 0, 1, 0, 0, 5, 1. Yeah. So the easy way to remember this is, you see this 2, 3 here, right here, this subscript 2, comma 3. Basically what you want to do, you want to go into your second row, third column, and that's where the 5 is going to show up. So you start off with the identity, and you go in the second row, third column, and you just stick a 5 where that 0 would have otherwise been. So for example, if I wanted to do real quick, R 1, 2 of 7. I start off with the identity, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. And then I go in the first row, second column. So where's that? Right here, right? First row, second column. And I'd erase that entry. First row, second column. And in place of that 0, I'd put a 7. Well, that would be R 1, 2, comma 7. That's the quick way to do it. Oh, I forgot to give a columnar definition. So I gave a verbal definition. Let's actually write it in column form. R, it's a hard one to write. Ij of R. So epsilon 1 is not going to change. Epsilon 2 is not going to change. Actually, epsilon I is not going to change. Remember what's changing. It's the jth column, right? The jth column. So we're going to go along to the jth column, and rather than having the epsilon j in the jth column, you're going to have R times epsilon I plus epsilon j. This is going to be the jth column right here. Jth column. And back here, this was the ith column. So no change to the ith column, right? It's the jth column, that this whole thing. R times epsilon I plus epsilon j is the whole jth column. And then it continues on normally all the way to epsilon n. Okay. So we probably won't use these column forms, but